Okay.
Okay, so quick close, have a look here. So here's the problem, second problem on the assignment, the third of the optimization assignment, short one. Look what it's asking here. It says a hunter is at a point along a riverbank, so H for hunter. That's where he's starting off, it's right there. Okay, he wants to get to his cabin, which is 4 miles north and 10 miles west. So he's got to go to the west and the north to get there. So here's the river. There's the river that he can travel along, right? And then this is the land up here. So he can travel 5 miles per hour along the river, but only 2 miles per hour on the rocky land. So he's going to be journeying along the river, and at some point, he's going to break away from the river and travel in a straight line towards the cabin. You get that? Okay, so we know that for this particular problem here, he's got to go 10 miles this direction and 4 miles that direction. But the thing that we can vary is, where does he, the only variable is, where does he leave the river and head off over the ground, right, over the land to get to his cabin. So you got to define a variable there. You probably, X would be the easiest one to pick, right? But what you know is that the time that he travels along the river is going to be determined largely by the speed at which he can travel along the river, and the time that he travels along the land is impacted by how fast he travels on the land, which is much slower, right? Does that make sense? Okay, so small hint. If we call this distance right here, that would be a good distance to call X, right? Reason being, if I want to break this up into pieces, so we've got the blue part where he's traveling along the river, and the orange part where he's traveling along the land, what's going to be that distance along the land by Pythagorean theorem?
Plus 4 squared, square root of x squared.
Okay, so square root of x squared plus 16 in this case, right? And the distance he's traveling along the river?
10 minus x.
If we had called this distance x, then I would have had a 10 minus x there that I'd have to square in the Pythagorean theorem, and that would be a little messier, wouldn't it be? Right, so wouldn't it be easier here to just call that x because we have to end up squaring it, right? Okay, what's your domain going to be for x?
0.
I mean, you could, if x is 0, that would mean he's just going to travel along the river the whole way and then just cut due north to his cabin, right? He'd be pretty dumb to go like further along the river and backtrack. We'll just assume he's not that dumb, right, that he's not going to do that. So 0 would be the smallest value x could be. What would the biggest reasonable value be? 10. Yeah, if he just immediately cut cross country. Okay, do you think one of those is going to be the answer probably? Probably not. Probably not. So somewhere on that interval, it could work out that way, but somewhere on that interval, we're going to have to determine, what's the value that minimizes time, okay? So we talked a little bit about this yesterday, but the total time, called capital T as a function of x, right? It's going to be broken into 2 parts. We're going to have the time along the land plus the time along the river, sorry. That was blue, wasn't it? Time along the river. Plus the time along the land. And I can just write both of those expressions in terms of x. And then all I've got to do, then I've got time as a function of x, and then I just make my table in short town. Right? Get the idea? Okay, I've got an example that we could go through. Tell you what, I'll kind of hold off on that. I'll hold off on that. Well, if we have time, we'll go through it at the end. Okay? But this is just a harder version. There's some really cool physics that comes out of this. I was kind of hoping to have an excuse to do this problem, because it turns out it gives us, well, I'm not going to spoil it for you. When we're all done, we can look at the physics. Have you guys done optics yet, physics?
Yes.
So you've looked at like refraction and reflection and things? Okay, so you've looked at, you guys have looked at like Snell's law?
Yes.
Okay, all right. All right, so here's what I want to do though. I want to look at a couple economics applications. Because that's another really big application of optimization is in economics, right? Where we're trying to do things like maximize profit. Okay. So first of all, just kind of really simple economics. What is profit? Can you think of what profit is? I mean, it's
Gross pay minus the expenses.
okay. So it's going to be what we would call revenue, which is the total amount of money you've got coming in minus costs, right? The money going out, and hopefully that's a positive, right? Usually that's what we're shooting for in business. We want the positive number to be the profit. So profit equals revenue minus cost. And so that's what we're going to come up with here. We want to maximize profit, so we have to come up with some kind of a profit function. But to do that, we got to think about what's going to be, what's going to be the revenue and what are going to be the costs associated with a problem like this. And this is a really common, it's a simple problem, but this is a really common kind of an economics application because you see things like this all the time, where you've got we're going to set what's called a demand function, which is, this is just basic macroeconomics. As you increase the price of something, the demand tends to go down, right? Now there's some weird cases where in some niche markets you can actually do the opposite. By increasing the price, you make it seem more exclusive, and sometimes people will actually, that's a great market to be in. If you're selling the thing where you can increase the price and that increases demand, that's a pretty good situation to be in. But that's not normal. So in this case, this real estate office handles 50 apartment units. When the rent is set at $720 per month, that's going to be just the amount where all the units are occupied. Okay, we wouldn't want to reduce it below that because they're all occupied. All 50 are occupied. So if I decrease the rent, they're going to stay occupied, but I have less revenue coming. Right. So that's the smallest, or that's the largest rent we could charge and have all the units occupied. But what we find is, we've taken a look at, we've kind of varied the monthly rent charges, and what we find if we look back at the data is, on average, for each $40 increase in rent, one additional unit becomes vacant, right? So based on our research, that's what's happening. Each occupied unit requires an average of $48 per month for service and repairs, so what rent should be charged to obtain the maximum profit, okay? So we're going to define what's called the demand function. Now the demand function is going to be price as a function of X. So what's for the small p, this is lowercase p and that's big P. So this is the price per unit item, right? So in other words, what are we going to charge for each unit? What are we going to charge for rent, in other words? Okay, we have to come up with some relationship here between the number rented and the price. Well, that's given to us. That's given to us right here. Here's the information that's important. When it's $720, all units are occupied. For each $40 increase in rent, one additional unit becomes vacant, right? So if we thought about that as like a linear equation, for example, right? Where we're going to have, for example, we could do, like if we were going to plot something like P, lowercase p, as a function of X. We just have some data points, don't we? Right? When the rent is $720, so when the Y value is $720, the number of units occupied is 50. So we just get some data point out there with coordinates. 50 units are occupied when the rent is $720, right? Let's pick another point. Well, we know that if we increase the rent by $40 up to $760, how many units are going to be occupied? 49. So we're going to get some other data point up there, which is going to be 49, 760, right? And this is supposed to be I didn't put that in a very good spot, did I? But that's a linear function. So that's gonna be our demand function, that's the relationship, but we just wanna turn that into the equation of a line. We can do that. If we just do something like, what's the slope gonna be here? The rise is gonna be, to go from point to point, my rise is gonna be negative $40 per 1 unit, right? If I'm gonna rise by negative 40 and run by 1. So my slope is negative 40. And I could use either one of these points. Let's use that one. And I'm gonna get P minus, instead of Y minus, I'm gonna get P minus 720. Just using the point slope formula, equals negative 40 times X minus 50. And I can come up with a function here, can't I? All right? I end up with P minus 720 equals negative 40X plus 200. If I add 720 to both sides, I get P equals negative 40X plus 920. Okay, does that make sense? So there's P of X. Okay? That looks good. So there's my demand function. That's the price per unit, right? That our data tells us, that's the relationship. The price per unit is given to us by this function. It's a function of X. The number of units rented is related to the price in that way. So then what's our revenue going to be? If lowercase p, the demand function, tells us the price per unit, and X is the number of units rented, what's our revenue? What's it gonna be? Well, this is the amount we're charging per unit. So this would be in terms of like dollars per unit. Dollars per apartment. The number of apartments rented is X.
P of X times X.
There you go. P times X, right? Demand function times X would be revenue. Okay, so profit equals P times X, lowercase p times X, right? Now, what's my cost gonna be?
48 X.
Yeah, 48 times X, because this is the amount that we're paying for service and repairs for each occupied unit. The number of occupied units is X, right? So we're just gonna subtract 48X. Okay, does that make sense? Questions on that? So this is the amount of money we got coming in, this is the amount of money we got going out, okay? So this really now, this just becomes, oh, and what's our domain gonna be?
0 X.
No, it can't go to infinity. X is the number of, the independent variable is the number of units occupied. So 0 up to full occupancy, which should be 50. Right? So there's our function. Now we can go ahead and plug in for P though. We know that the demand function is negative 40X plus 920. So we can go one step further. P of X equals X times, let's write that as 920 minus 40X, how about? Minus 48X. You guys see that? Okay, so there's the profit function. Let's just take a picture of that, and now we can scoot over to the calculus page where all we're going to do is make our table. Question? Yeah.
So on that previous page, the demand function,
Yeah.
if you plug 50 in for it, did it get?
We should get, if we plug 50 in, we should get 720, right?
No.
Oh, which did I?
Is it 40 times 50? Yeah, it's negative 2,000.
Oh, 2,000. Whoops, yeah, I screwed that up. So we get 2,000. Oh, yeah, you're right. You're right. So let's fix that. So that should be a 2,000. There we go. and we add 720 to that, we get 2720. That's better. Alright. Okay, now let's verify that works. So if I plug in 50, I'm gonna get, I get 720, right? Does that make sense? Okay, and if I plugged in 49, I would get 760. Yeah, that works. So I gotta fix that up here then. So that should have been 27. I knew I kept you around for some reason, sure. And we already said our domain is 0 to 50, right? So all we gotta, now, do we wanna differentiate that as is?
No.
We wanna expand that for sure, make it a polynomial. Right. So if we distribute the x, we're gonna get 2720x minus 40x squared minus 48x. So if I combine like terms, p of x equals, what's that give us? 2672. Is that right? I think so. X minus 40x squared. Is that right? Okay. Yeah. Okay. So we can differentiate this. What's that going to give us? Yep. Yeah. So if we differentiate that, what do we get? 2672 minus 80x. Okay, so then, and if we take a second derivative, what's that? Negative 80. The important thing being it's negative, right? So now we know that p prime equals 0 when x equals 2672 over 80. What's that roughly equal to? Somebody, what's 2672 divided by 80? What is it?
I got
33.4? Okay, so it's about 33.4. So we would want to, we can't rent a partial unit. So what do we probably do with that? Is it closer to 33 or 34? 33, so we would probably say 33 units is what we want, right? But we're just trying to set a price anyway, aren't we? Right? So never mind. If we're just trying to set a price, we might as well plug this value back into my demand function, right? Because that's all we're trying to do. Oh, we got to verify, I guess, that this is a maximum, but we know it is because the second derivative is negative. So if I made a quick table, so there's our critical number. We get a 0, we get a minus second derivative. So horizontal tangent, concave down, that's our maximum, isn't it? Right? So that's the value, that's the number of occupied units that's going to maximize our profit, right? And so we could just plug that back into our demand function to figure out what's the price that goes with that value of x. And that's where we'd set our price to maximize profit, our price per unit, okay? Get the idea? So it's a pretty simple example, but that's why calculus is such a big part of economics, quantitative economics. Okay, what about one like this? You assume that the amount of money deposited in a bank is proportional to the square of the interest rate the bank pays on this money. Okay? Furthermore, the bank can reinvest this money at 12%. Find the interest rate the bank should pay to maximize profit. So we'll just use the simple interest formula. Okay? So think about that one for a second. Okay, see if you, just take a second and see if you can think about how to set that up. So how's this work then? Let's look at each of these statements and let's see what this means. So assume that the amount of money deposited in a bank is proportional to the square of the interest rate the bank pays. How do I say that? So let's define, if we define X as the amount deposited in the bank, and we're going to define I as the interest rate paid by the bank. Okay, how do I set up that relationship? So the amount of money deposited in the bank, that's X, is proportional to the square of the interest rate paid.
X equals I squared.
You can't, Ki, good, Ki squared. Okay, so we could say that statement would be X equals Ki squared. Okay. Furthermore, the bank can reinvest this money at 12%. Okay, so what's that mean? The bank can reinvest it at 12%. What's that mean? How much is, how do we calculate the amount that the bank is making off of the amount of the investments? So here's that statement. That's going to be the revenue, isn't it? Right? So what's the revenue function going to be? If X is the amount that's invested in the bank, how much money is the bank bringing in? 12%. Okay, so that's going to be like 1,2 X is the amount of money that the bank is making, right? How much is it paying out? Here's the interest rate paid by the bank, right? So it's going to be X times I. Everybody agree? So the cost function is the bank is paying out X times I or I times X. Right? Everybody see that? And so the profit, if we want to figure out how we're going to maximize profit, we just want the revenue minus the cost. So the profit function is going to be 0.12x minus I times x, right? Okay, but we have to write this all in terms of x. We've got two variables there. But here is our secondary equation. There's the relationship that relates x and I, right? So if we solve that for I, well, actually, we're just going to multiply I times x anyway, right? And so what's that going to give us?
You can always substitute back for
You could, right, you could just, but what we want to get, oh yeah, we're trying to find I, aren't we? Right, right. So we want to find the interest rate the bank should pay to maximize profit. So we're trying to figure out what should I be. So that's going to be our variable anyways, and not x. We want P as a function of I. What's the interest rate we pay to maximize profit? So now we can just make this substitution and look what we get. And while we're at it, we could even factor out an x here too, couldn't we? Right? So we could make this 0.12 minus I times x by factoring x out. Right? And there's my x. Although we want to make this a polynomial anyway, don't we? That's kind of a dumb idea. Skip that. So 0.12 times x minus x times I is going to be minus 0.12 times x, which is ki squared. We're just going to go from there. Minus I times x. Okay, and there we're going to get a function with only i's in it, right? So we get p of I equals 0.12 k I squared minus k I cubed, right? What would be a reasonable domain for I? We probably don't want to charge a negative interest rate. We want to make some money. Right? So anything above 0. Okay. Now we just do calculus. So what's P prime? K is a constant, right?
0.24
Okay. Minus
3 ki squared.
Okay. And while we're at it, if we calculate second derivative,
0.24
minus
6 ki.
okay. And so when is, let's figure out when P prime equals 0. So P prime equals 0 when this whole thing equals 0, right? When 0.24 ki minus 3 ki squared equals 0. Well, for one thing, we could divide both sides by k, get rid of that, right? We could factor out an I. So we get I times 0.24 minus 3i equals 0. And so we get two critical numbers. What's one of them? 0. That's probably not good though, right? That one's probably not going to pan out. How about this one? If I solve that, I'm going to get 3i equals 0.24. So if I divide by 3, I equals 0.08. Okay, well that's not even in our domain, right? We can just get rid of that one. But that one is. So let's make our, let's make our table. So at 0.08, we got a 0 of the first derivative. What do we get for the second derivative? If I plug 0.08 in there, I'm going to get, we could get rid of the, we could take the k out, right? So 0.24 minus 6 times 0.08, that's gonna be negative, isn't it? Right? Is that what we want? Right? Negative means we're gonna get horizontal tangent, concave down, so that's our maximum for profit. Okay, we get that when we set an 8% interest rate. We're maximizing our return. Okay? So you get the idea. I mean, that's, whenever you're trying to calculate a profit, it gets more complicated because these are pretty. I mean, you probably find that there's this exact proportionality. No, probably not. Probably not. When you fit the curve, you're probably getting something much more complicated than that. So you end up with some boundary value differential equation that these quantitative economists are solving that's going to be significantly more difficult calculus, but you probably don't even do it analytically anyway. You're probably going to do it using technology anyway. But you got to be able to set the calculus up. That's really, when it comes down to it, after you take all your math classes, very seldom are you going to sit down and solve differential equations by hand. You're going to use a computer algebra system, but you just got to know how to set them up. Right? That's where knowing the calculus comes in.
So this is the kind of mathematics that I guess you could use to control profit.
It's the kind of mathematics that any big money-making entity would use if they're going to control, if they've got something that they can control that impacts, profit, that they're going to try to pick a model that's going to inform their decision about how they set that value, right? So they can make the most money. And it gets a little more complicated than that because sometimes you'll even sacrifice profit if you can be in a place where your profits are increasing when you want to be in a safe part of the curve. So that's where the inflection points come in. You want to be at a place where the rate of change of profit is always going to be positive if you miss by a little bit. So sometimes people make the mistake if they want to maximize profit, but their models are a little bit wrong. And if they overshoot, if it plunges them into a steeply declining profit function, actually they may not be smart, right? You want to be a part of the curve where typically you want to be around an inflection point where you're still increasing. And so there's a whole, if you study economics, which I really haven't done, I don't know that much about it. But if you study economics, those are the kinds of things that you kind of meld the math with sort of financial strategies based around, what are the implications of being wrong here? Because the implications are real. It hits you in the pocketbook, right? And so you look at it a little differently than you would if you were applying this in an engineering sense or in a biology sense or something. But I think it's interesting. People that do this make lots of money.